All right, well, we are going to get started here with the Keys to Anaerobic Digester Stability presentation. I'm Dan. I work over in Aquafix Labs. Aquafix Laboratories is a lab where we do a lot of research into common wastewater problems, and we do a lot of troubleshooting, and we do some custom testing for customers. But primarily, we focus as a research lab solving wastewater problems that come to our attention. So if you have concerns or questions or unusual things going on at your wastewater process, please make sure to send them to us maybe after the presentation via email, because we always like to have more issues to solve in wastewater. So today, I'm going to go really quickly through what we're covering. We're going to do some anaerobic digester basics, talking about nutrient balance and things like that, then symptoms of healthy or unhealthy digesters, causes of poor digester health, how to prevent an upset, operational changes in Aquafix products, how to handle an upset digester, and managing upsets with Aquafix products. So now we have our anaerobic digester basics. So we're going to cover how the process works, keys to having an effectively functioning anaerobic digester, a couple good and bad things that you need to watch out for when managing your anaerobic digesters, nutrient requirements, and types of systems we're going to cover. So anaerobic digestion is a some people say 5-step process, and it takes place in these 4 to 5 steps. We have disintegration, breaking up of large solids to small solids, hydrolysis, which is converting these small particulate solids into soluble material which can be metabolized by bacteria. Then we have acido and acetogenesis, which is the process of acid generation, which is producing food for acetoclastic methanogens in methanogenesis. So disintegration, because I love ice cream, I'm going to use this as an analogy. You could have you could be making a milkshake or a malt. You can blend it up. It's not going to fit through your straw if you don't have adequate mixing and disintegration taking place. And that's where my analogy falls apart. There probably were better analogies, but I felt like mentioning ice cream, especially because it is finally starting to get a bit warmer in Wisconsin, though that may only last a couple of days. But I've been thinking more about it. So then we have hydrolysis, which is performed primarily by facultative bacteria, which produce exoenzymes, which convert these insoluble materials like fats and proteins and complex carbohydrates into things like sugars, amino acids, and fatty acids. Now, the fatty acids go through an additional digestion process where they're converted from long-chain fatty acids to short-chain fatty acids in acetogenesis. This process happens 2 carbons at a time. They're chopped down into more and more acetic acid, which is converted to acetate in acetogenesis. I don't really like referring to those as separate steps for a number of reasons. 1, acetogenesis is a fairly short process, and 2, the words sound so similar that it ends up being very confusing in a presentation. All right, so then we have methanogenesis, which is performed by generally 2 groups of bacteria. You have the acetoclastic methanogens, which use acetate to produce methane, and you have the, I hope to only say this word once because it really does not flow off my tongue very well, but hydrogenotrophic methanogens. And these 2 communities work together because the hydrogenotrophic methanogens are removing hydrogen and using carbon dioxide to produce additional methane. They're going to clean up your biogas, and they're also going to prevent an accumulation of hydrogen or hydrogen sulfide. So the better your hydrogenotrophic methanogens are functioning, the less likely you'll have sulfide reducing bacteria or sulfur reducing bacteria in your process thriving and competing with our methanogens. So we have 3 key parts here: agitation or mixing. Ultimately, this doesn't mean you need a ton of mixing in every process. It just means that your agitation needs to be good enough to handle your hydraulic and solid retention times. The more agitation you have or mixing, the more efficient your process is going to be. You also open the door if you mix too much to things like foaming. So it's important to find a balance for your specific process on how much mixing you need to get everything breaking down properly. And obviously, some things like a lagoon can get away with a lot less mixing because they have a lot more time. The other thing is considering our 2 dominant communities of bacteria that we're concerned about in anaerobic digesters. We have our acid-generating bacteria. and our methane generating bacteria. Now, I have a 20-month-old toddler at home, and this is a reasonable analogy here. We give her food every day for every meal. She generally eats quite a bit, but if you give her too much food, that food does not go into the toddler. Mira does not eat the food. It begins to show up in different spots around the house, just kind of randomly. Now, what would you expect would happen to the food that's just laying on the floor because Mira decides not to eat it and throws it somewhere? Well, most likely in our house, it will be eaten by our dog. And you don't want your dog eating too much food that is not dog friendly. It can lead to bad things. And your digester, if you have too much acid, you're also going to have bad things taking place. All right, so just cover a few of the advantages and disadvantages of anaerobic and aerobic digestion. So anaerobic digestion, generally, if it's working well, has less energy input because gas generation provides fuel which can be used to heat the digester and generate electricity, and there's no need for aeration. So if you have a digester producing a lot of healthy biogas, you rarely need to put a lot of energy into it to do anything with the digester. It also does a generally better job of reducing solids because anaerobic digestion is a better complement as a process to an activated sludge system because your aerobic bacteria have already had sort of an effort to degrade the waste, but your anaerobic bacteria have different methods for degrading waste, and some substrates are easier to eat anaerobically than aerobically, and vice versa. So it tends to be complementary. However, you don't see many of them in very small systems because digesters are expensive to build and design, and generally speaking, the costs do not go up linearly as you scale up the volume of the digester. So you could put a lot of money building a small digester that hardly produces any biogas and doesn't do a whole lot of good in terms of solids reduction relative to your total solids produced throughout the year, and it isn't able to compensate for the increased cost. But once you start to see mid to larger sized wastewater treatment systems, or you have industrial systems with specialty waste which digests very well anaerobically, usually these are very high strength waste streams, then you tend to prefer an anaerobic digester, assuming you can keep it running stably. All right, so we have some optimal conditions for all anaerobic digesters. You have the mesophilic digesters and the thermophilic digesters, which typically thrive in 95 to 95 degrees Fahrenheit for mesophilic digesters, and 125 to 135 Fahrenheit in thermophilic digesters. You also tend to have a solids retention time about 3 times longer in a mesophilic system versus a thermophilic system, to give you an idea of how much more efficient a thermophilic digester can be. You also have an ideal pH of 6.8 to 7.2. These temperatures and ranges are significant because, one, methanogens are fairly slow growers. You need to have time for them to produce fully in the sludge in order to degrade your substrate. And two, the further you go outside of this range, the less methanogens are able to degrade the substrate because methanogens, a fairly narrow range of organisms there, and the further you get from this optimal temperature and pH conditions, the less of them will be doing anything. So you might end up at pH 6.5 with only a couple methanogens producing methane at that point, and the rest will just be sitting there, being a bit lazy, not doing anything useful. All right, so next thing I want to cover is nutritional requirements. We have our macronutrients to start off, which are primarily grouped as COD, phosphorus, nitrogen, iron, and sulfur, maybe. COD is really referring to carbon loading in these cases, which would be looking at things like fats and sugars. All of these compounds are necessary for cell metabolism, but iron and sulfur less so, and phosphate less so, quite a bit than the other ones. Now, an interesting note, in aerobic conditions, you have a fairly well-established 100 to 10 to 1 to 105 to 1 range of BOD to nitrogen to phosphorus, which tends to work very well. Anaerobic digesters tend to be more varied, and they tend to use a lot more carbon. So you might see as much as an 1,000 to 7 to 1 here, or 250 to 7 to 1. We're talking like 10 times more carbon relative to nitrogen and phosphorus in many cases. So a lot of the times you don't see nitrogen deficiency, but we have had a couple of systems bring up issues with nitrogen deficiency, and then you'd end up supplementing, similarly to any other system, to increase the nitrogen loading and help the health of your bacteria. Iron and sulfur are kind of borderline in terms of whether to consider them a macro or micronutrient. But typically, the higher your levels of sulfur, the higher your levels of iron you are going to want, because iron precipitates out sulfides, preventing an accumulation, and it helps to remove sulfates from the solution. And getting rid of sulfates is important because the less sulfate present, the less likely you'll have a sulfur-reducing bacterial community competing with your methanogens. So if you have high sulfur levels, you want to add more iron. In some cases where you have very low sulfur levels, iron can actually be slightly inhibitory and contribute to problems occurring in your process. But in the vast majority of processes, there's a decent amount of sulfur, which means you don't have to worry about supplementing too much iron. And in a lot of cases, the more the better. So then we have our micronutrients, iron and sulfur. Again, maybe, I don't know. It depends on what you want them to be, I suppose. But we also have our trace elements, which there is a whole long list of. I have a couple examples. Cobalt, molybdenum, nickel, you might have copper, you might have selenium, you might have manganese. Basically every metal you can think of in the transition metal column has some role to play in anaerobic digestion. Transition metals referring to the periodic table. So you basically have to keep an eye on these metal concentrations because you hardly need any of them for your process to function well, but in a lot of these cases you can end up with too much fairly easily, especially if you supplement, and too much of a trace metal is very likely to lead to toxicity, and they can also compound with other issues taking place in your anaerobic digester. All right, so we have a quick question. Is it best to consider an ideal C to N ratio in the influent rather than the COD to N to P ratio mentioned here? And so when I am mentioning it here, I am primarily looking at the COD to N to P ratio in the sludge feed. It's always nice to do analysis both for the influent and in the digester, especially in cases where you have variable loading, because unless you have a really good representative composite from your influent, you can be missing something like a metal that comes in at certain times but not other times, and it will sit in the digester long enough to have a contributing effect. Or you might have nitrogen coming in some of the time, and a lot of the time your influent sludge feed is low in nitrogen, but if you look in your digester, you'll notice there is an accumulation of nitrogen taking place, which means you don't have to worry too much about nitrogen deficiency. So I would say good to consider both, but generally the influent is a more important variable, assuming you have an ability to take a good representative composite or you sample regularly enough to have a good understanding for how your influent varies throughout the year. So a lot of people have questions about trace element supplements or trace metal supplements. We actually offer one, Biogas 1, which is kind of a general all-purpose trace element supplement. It is not a specialized blend which is produced specifically for one site, but it does contain trace elements adequate to supplement most systems. The trace element levels in your digester need to be evaluated for different things. There's a lot of companies that will produce trace metal supplements, and they will do measurements on your sludge and your sludge feed, look for levels of metals, and make recommendations as to a specialized trace element supplement in your process, and then they will provide you a supplement. Now, make sure the company you work with who does this has a good reputation and is well known, because it's very easy to just make a random metal supplement. But in cases where you are missing some specific unusual metals because of your specific process, having a specialized trace element supplement can be really beneficial. But in a lot of cases, we found our Biogas 1 works perfectly well for metal supplementations. So you can always try a couple things, see what works better and worse. The important thing is not to overdo your metal supplementation and to be aware of what levels of metals you have. So when you're measuring for trace metal concentrations in your digester, you're going to want to consider a couple of things, but one of the main things you want to look at is levels of soluble versus insoluble metals. And you can do this through centrifuging your sludge feed, or you can centrifuge your sludge, or you can filter the sludge. But the idea is to remove most of the solid's gunk, so you have a filtrate, and that gives you a more direct idea of what the soluble metals are versus insoluble metals. If you perform that analysis, there are some caveats here. Some insoluble metals may be bioavailable to bacteria present in your system, and some soluble metals may not be bioavailable to bacteria in your system. But generally speaking, the vast majority of the metals that are available to bacteria are soluble, and levels of soluble metals is a lot better indication of toxicity and oversupplementation or undersupplementation in your process than just looking at an unfiltered sample, because a lot of that is just gunk that's not going to contribute to your process. All right, we have a couple of more questions here. Are there toxic metals we should monitor for? So I'll answer that one first. Yes, there are toxic metals which could be monitored for. Particularly, most of the trace metals can be toxic at relatively low concentrations. So something like nickel or copper, all of them can reach toxic concentrations. But some that can be particularly toxic that have some beneficial properties in really low concentrations would be sort of the classics like cadmium, lead, that kind of thing. They're especially concerning if you see them popping up in higher concentrations in your digester, and can be toxic in very low levels when they are soluble. But I would just kind of do a broad metal measurement and look at the soluble metals, and that will give you a good idea of what you've got to watch out for. And you can take corrective action for the specific metals at that time. All right, one other quick question. There's a question about vitamin nutrients in microdoses can be beneficial. Yeah, there are some cases I have seen where people have supplemented vitamins and seen improved anaerobic digestions. I haven't seen a lot of specific data for what the vitamin levels were and what levels of vitamins were added, that kind of thing. But I have heard of vitamin supplements being successful, and this may be something to look into if you've looked at stuff like the trace metals and your overall nutrient balance and you're still struggling with your waste stream. So definitely worth keeping in mind, but I don't have any hard data for what people have typically done to handle vitamin supplementation in anaerobic digesters. So quick comments on thermophilic versus mesophilic digesters. Thermophilic digesters are much faster than mesophilic, and they have higher quality sludge product. Typically, I'll only see these in large processes with a very steady waste stream, because while thermophilic digesters are faster in every way, one of these ways is catastrophic failure. They are much faster with that. So your thermophilic digester, if you have a variable sludge feed, it is very likely to have a lot of issues. Interestingly, there was one case where we had a municipal facility which had thermophilic digesters, and they were feeding waste-activated sludge with high filament loading into it. And they would see foaming every time they fed their waste-activated sludge, but when you looked at the sludge sample in the digester, there were basically no filaments present, and the foam had already subsided most of the times when we got the sample because the filaments were breaking down incredibly quickly, but they were sticking around long enough to cause a day or two of foaming. All right, quick poll for everybody. What type of anaerobic system do you have? I want to get a sense for the breakdown of people attending the webinar. And for you who have others, definitely let me know what your other is. I always like to hear that. Let's see. All right, so our poll has a lot of complete mixed digesters is looking like, which this looks like about the breakdown I would have expected. A couple others, a couple UASBs, but mostly lagoons and complete mixed digesters. So good to know. Let's keep focusing on those complete mixed digesters, but I will talk about UASBs and lagoons. All right, so continuing on here, we have our types of anaerobic systems. Compute mixed, lagoons, and UASBs is what we're going to be covering here. All right, so our complete mixed we're starting off with is our most standard anaerobic digester. And I'm happy to see there are a lot of complete mixed digesters here because that is what I see the vast majority of when I'm working with them. They have effective mixing and are good at digesting solids content such as waste activated sludge compared to other types of digesters. So they're frequently used in municipal systems. They get good solids destruction. They typically have pretty good methane production. But they tend to be a little bit worse at handling high levels of soluble BOD than other things like a UASB because you are unable to control the hydraulic retention time very effectively in complete mixed digesters relative to solids retention time. So it's difficult if you have high levels of soluble waste coming into your complete mixed digester to be able to handle it all and maintain a sludge concentration that's appropriate for your specific plant. So next we have our lagoons versus complete mixed system. Lagoons are inexpensive to build. That's the main reason we see them. And I've traditionally thought lagoons may have many mixing issues, but a lot of lagoons do function very well relating to their high holding times and large volumes. They can make up for a lot of their deficiencies in mixing. And for industrial waste, they tend to be a very effective solution for removing a lot of COD for a relatively low cost. And some of them are able to use biogas, their biogas, though it tends to be more difficult to collect and generate. So you have a slow treatment time. The other thing to watch out for in your lagoons is since you have limited mixing, typically you end up with channeling occurring, which produces a channel directly from the inflow of your lagoon to the outflow of your lagoon. And if you have channeling taking place, you get this flow through going on, which dramatically reduces your treatment volume because the liquid will go straight through the channel. All right, finally we have our UASBs, which are great for dealing with high levels of soluble COD because you have a lot of HRT control. You can recirculate the liquid at a faster rate, and you'll end up with a very effective treatment time. But these are not good for treating high levels of solids because they rely on having very dense granule formation. And if you have solids coming into your process, they become integrated in the granules in many cases and lower the granule density, which can cause them to be washed out of your system. Since UASBs are very slow to grow granules, this can be incredibly hindering because it may take months to regrow granulation once you have it, sometimes years if you don't have an ideal substrate. And you'll probably need to find UASB granules from an additional source, which can be difficult because there aren't very many of them. All right, few quick notes on UASBs. I have a number of questions come up over the years on what a good upflow rate is, and ultimately that is determined by your process. Typically, I see a lot of systems in the 0.31 to 0.46 meters per hour range, but they can be over 1.5 meter per hour, and it does vary widely. That is a good thing to play around with and consult with your engineer on site in order to figure out what the ideal upflow rate is. Because if you have a high upflow rate, you can form larger granules, or you can wash the granules out of your system. So you got to wash out. All right, so a couple bits of helpful testing for monitoring your anaerobic digester. Biogas testing is great. We like to look at methane versus CO2 concentrations. Also keep an eye on those sulfides present. If you're seeing like 1,000 parts per million sulfides, you can bet that your digester could use some effort to precipitate out some of that sulfur to prevent that, because that's going to mess with the ability of the methanogens to do their job. So 60 to 70% is considered really good for biogas. Below 60% tends to be mediocre. A torch color is a pretty good indicator too. It's always nice if you can make more use of your biogas than burning it off. But methane torch color, if it's a nice blue and difficult to see flame, that's generally good. If it's a big orange flame, that's generally bad. And keep an eye on this because this is a really sensitive indicator to a problem in your anaerobic digester. So if you start to see this deteriorate, it might be a good time to start adding something like bicarbonate to your system in order to stabilize the pH a little bit before you see the pH begin to drop off in your system. Volatile acid to alkalinity testing is also a nice sensitive indicator for an upset in your anaerobic digester. Typically, the ratio should be below 0.34 parts volatile acid to alkalinity. If you see it above that, you have a much higher risk of having your pH drop. Ideally, the ratio should be around 0.1. Exceptionally high volatile acids and alkalinity level can also be a problem, so it's nice to have this data as well. Where you increase the likelihood of foaming if you have very high acid or alkalinity levels, because both of these can contribute to reducing surface tension, which I'll talk a bit more about later. Of course, you can also run fatty acid analysis. It's really nice to get a speciation of fatty acids as a diagnostic tool if you're having problems getting your digester to run quickly. And in these cases, you can look at the ratio of long to short chain fatty acids. And if you see an accumulation of long chain fatty acids, that typically indicates your digester is being overloaded, or you're having an issue with hydrolysis or mixing being inadequate. And if you see an accumulation of short-chain fatty acids, you can be relatively sure that is a problem with your methanogens, and you're able to treat these accordingly. I mentioned metal analysis already, but that, of course, is nice to run every once in a while on your feedstock so you get an idea of what's going on. Same thing with general influent loading. And another interesting tool, if you are attempting to correct or supplement your anaerobic digester, is a BMP study, which tends to be fairly simple. You fill a jar, you have to be able to measure gas and mix it for a full month or so. But essentially, you're filling little bottles with anaerobic feed sludge and a anaerobic culture, and over the course of the month you can compare how the methane quality and quantity has varied depending on different additives, because it can be very slow testing them one at a time in your process. This enables you to experiment with a bunch of different changes in your process at the same time to measure how they affect methane, which is a very good indicator of anaerobic digestion efficiency. Okay, so now we're going to go over a few problems occurring in anaerobic digesters. Acidification would be a main one that we see a lot of the time. If the pH starts to drop, that's very concerning. Loss of biogas generation or poor biogas generation is another one. Toxicity, sludge volume expansion, and foaming. Foaming probably is the most common issue we see. So acidification, this is where you have volatile acids increase in your digester, and this causes the pH to drop. This is a process that leads to a whole bunch of different things, which is why it's important to do that volatile acid to alkalinity testing. You don't want your digester to begin to acidify. Do you remember earlier I was talking about metal concentrations in the digester? Well, levels of soluble metals will increase as acidification increases. Which means you're more inclined to have metal toxicity. The lower the pH gets, the less methanogens are able to function, which tends to make this problem as well. So you tend to get this snowball effect occurring where it just gets worse and worse and worse. And eventually you hit this acetic acid buffered zone, which buffering is referring to stabilizing of the pH. At around pH 7, you have a lot of bicarbonate buffering taking place, which is great. It'll maintain a healthy pH in your digester if you have decent levels of bicarbonate. But if your pH gets to this 4.5 to 5.5 range, you're acetic acid buffered. Now, this is important, and it's a difficult concept to explain in a lot of cases, because adjusting the pH in a buffered zone is much, much harder than adjusting the pH in an unbuffered zone. And it can be really confusing and misleading and a problem, especially if you're supplementing your pH with something like caustic soda or sodium hydroxide, for example. And that's because you might add 50 times more getting the pH to go from like 5.3 to 5.5 than you would to get the pH to go from 5.5 to like 9. So you have to be really careful once you're adjusting the pH with a strong base like sodium hydroxide, because your pH will very likely start to spike in this 5.5 to 6 range, and then you can end up with your digester being really messed up and things like ammonia toxicity taking place, and it just can be a real mess. And then you have a lot more time potentially it takes for your digester to fully recover. So proceed carefully once you hit a neutral pH and begin adding something with more buffering capacity or less strong of a base once you're getting close to pH 5.5. And it's nice to add those simultaneously with the sodium hydroxide at first, so you start to establish a bicarbonate buffering capacity around 7, because your pH will not increase as quickly either if you have a lot of bicarbonate present. Loss of biogas production can be a really confusing problem because it can occur for a wide variety of reasons. These could be related to your waste substrate just not being great at certain times. Methanogens in general are quite sensitive to toxicity and have slow growth rates. And they tend to get really lazy if they don't like the conditions. So your methanogens might just go ahead and take a nap during certain times because they don't like something, like maybe you have more sodium come in than normal. And then you lose biogas for a couple days. And then if that goes on for a period of time, you have to go back and worry about acidification. Sulfur-reducing bacteria can also reduce methane production by competing directly with methanogens, which is another thing to watch out for. So we have some toxicity statements here. So ammonia I mentioned with toxicity. This is kind of an interesting toxin because ammonia, NH3, is toxic to a lot of digesters around 50 ppm. But ammonium, NH4+, is not toxic until over 3,000 parts per million in many cases. And as your pH increases, the concentration of ammonium converts to ammonia. So once you hit around pH 7.5, if you find yourself with over 1,000 parts per million of ammonium, you have to start being very careful with your levels of ammonia that may be starting to accumulate in your system. An accumulation of ammonia can start to inhibit methanogens. You can lose a bunch of your methanogens and end up with a volatile acid buildup, which will eventually correct the pH, but will set your plant way back. Trace element toxicity, I mentioned these tend to be more concerning at lower pHs, but it is important to measure the levels of soluble metals in your process because it's difficult to predict exactly how the chemistry is going to work in a specific digester. So taking these measurements can avoid speculation as to how much metal is soluble versus insoluble. And of course, sodium is another thing people are concerned about with toxicity. And the nice thing about sodium toxicity is that plants can acclimate very well to high levels of sodium. But in the short term, if you perform a pH adjustment in a digester that's already stressed out, that is not used to high levels of sodium. So example, you add a ton of sodium bicarbonate to adjust your pH. You can end up with a case where your sodium levels cause toxicity and they sort of inhibit your digester's ability to recover, which can prolong the upset, and you can end up raising your pH and having it drop again and raising it again and having it drop again. And you can fight with that for weeks or months in some cases. And eventually your digester will come around, but it's important, if you're noticing that sort of phenomena, to consider, am I adding too much sodium to my digester? Should I be supplementing something else, like a magnesium-based salt, or a calcium-based salt, or potassium? Because if you diversify the cations you're adding to your digester, like sodium, potassium, magnesium, then you're less likely to have this phenomena where you keep adjusting the pH and then the pH drops back down, which can be a real mess. So foaming, I mentioned it's probably the most common issue we see in anaerobic digesters. And that's because anaerobic digesters are just great at producing foam. Just a random idea, I was very excited today because I purchased a Roomba. Because we have toddlers around, I don't want to have too much dog hair accumulating on the carpet. We're just really busy. But nobody has ever created a Roomba for anaerobic digester foam. So maybe somebody else, if you want to bring that idea to one of these robot vacuum cleaner things, maybe we could have a robotic foam cleanup tool, because I know many operators do not enjoy the process of cleaning up a major foaming event. And we've had some sites where foam just totally covered their plant and it's a real mess. But anyway, foaming and sludge volume expansion are two similar processes and they lead to similar problems, but they tend to work contrary to each other. So sludge volume expansion is referring to biogas accumulating in the sludge layer, causing it to balloon out, whereas foam is biogas accumulating at the surface of the digester. Now, a lot of people, in the case of foaming, you can decrease the mixing, you'll have a little less agitation, and that tends to decrease the amount of foam, and especially in complete mixed digesters. But if you decrease the mixing too much, then you can end up with sludge volume expansion, which is a much more annoying problem because it's less likely to respond to a defoamer. The higher the solids environment present, the less likely a defoamer is to work. So when you're decreasing mixing to correct a foaming event, Be very conscious of this sludge volume expansion issue. You need to have enough mixing for this to keep taking place because you'll see the exact same problems in many cases. They'll just be a little bit harder to solve. But foaming, of course, is the more common issue. So foaming occurs when you have a mixture of surfactant, solids, and biogas accumulating at the surface of a digester. Sludge volume expansion is when gas is trapped within a digester, and both problems can lead to major safety and operational problems, such as poor ability to collect biogas, issues with your recirculating pumps, poor outflow quality, that kind of thing. So the foam formation, I want to go through this fairly quickly. You have a combination of surfactants, gas, and solids, which are present in every single digester. Digesters, in fact, are actively producing surfactants all the time in the forms of volatile acids, which is necessary for everything to work. But if levels get too high, such as really high volatile acid environments, you start to have the likelihood of foaming increase. The more gas production you get, the more likely foaming is to increase. And the higher the solids content, the more likely you'll have a very stable foam and a foam that's a problem for long periods of time. A lot of the time, foaming is the worst immediately after you've had digester souring and you begin to correct the pH, because you'll have a lot of volatile acids accumulated, and then you'll begin generating methane and carbon dioxide once the methanogens start working again, and then you get a big foam. And to make matters worse, a lot of the time, if you're supplementing something like sodium bicarbonate, you might have some foaming occurring as a chemical reaction with the acetic acid present in the digester. So here's just a quick overview of how surfactants work. You could have a nonpolar surface compound, which would be not really qualifying as a surfactant. Surfactant is generally a soap. There are some amphiphatic compounds which are not soaps, which can act as surfactants, such as volatile acids. But the worst surfactants are ones that are that have a nonpolar end and a polar end of the molecule. The nonpolar end tends to want to be excluded from the water, so you get things like micelles, which would be little bubbles of these nonpolar or polar groups on the outside and inside. But at the surface of your digester, you'll see what we see in this diagram, where these polar heads are below the surface and the nonpolar heads are above the surface. And these interfere with hydrogen bonding in the liquid, in the digester, so water. And generally speaking, hydrogen bonding causes foam bubbles to rip apart, which causes the foam to collapse. So if you have a lot of surfactants, hydrogen bonding gets inhibited, which means the foam begins to accumulate faster and faster, and this will happen in a lot of digesters. So generally speaking, foaming is caused by a mix of a variety of different causes. Of course, biogas production, solids, and some surfactants are always going to be present. But something like filaments could make the whole situation worse, or if you have higher than ideal solids, you might have a more propensity for foaming in your process, because all of these will form a thicker and thicker matrix at the surface of a digester in order to entrap biogas. All right, so what can cause a foaming event? Unfortunately, a lot of things can cause a foaming event. Temperature changes are a big one here in Wisconsin. These winters, if your digester pH drops by 5 degrees Fahrenheit, you can already have a messed up digester, which will become especially bad if you quickly raise the pH back up to 95 without giving the time for the methanogens to become happy again. Organic loading changes. Variable loading is definitely a big issue with digesters. We'll see a lot of these food processing digesters accept a really varied substrate depending on what happens when the food shows up. And you have this issue where if you don't have proper holding and equalization time occurring, you end up with really high loading sometimes and really low loading. So you end up with the cycle of the acetogens will start, or acid generators will reproduce quickly, produce a bunch of acid, and then the methanogens will be stuck trying to catch up all the time. And that's just difficult. Third one you have is mild toxicity, which would cause a foaming event. You could, of course, have major toxicity, but a lot of the cases of toxicity in anaerobic digesters are what we'd call mild toxicity. They're not killing the vast majority or a large portion of the cells present. But unfortunately, all of these problems can lead to the same symptoms, so it's very important to keep details of your loading, temperature, and that sort of thing, so you can understand what's going on when a problem pops up. All right, I want to cover filaments because these come up fairly often. We get a lot of samples sent to our lab where people are curious about filaments in their digester. And the most prevalent filament we have seen is Microthrix parvicella. So filamentous organisms in anaerobic digesters, they generally are not organisms that grow effectively in an anaerobic digester. Most filaments that are present in wastewater are strict aerobic bacteria, and these strict aerobes begin to die when they're present in an anaerobic digester. But some of the filaments, particularly Microthrix, can perform some limited metabolism, it looks like, and at the very least can survive dormant in a digester for approximately a month in a mesophilic digester, which is plenty of time for them to accumulate and cause a foaming event. The nice thing is these filaments are generally not going to grow in the process, which means you can look directly at something like waste-activated sludge or another feed substrate and say, that's where these filaments are coming from. I need to address the problem at that point rather than have it feed into the process. Another interesting thing is filaments in an anaerobic digester tend to be more difficult to identify because they're not in optimal conditions. One thing you do to identify Microthrix is a gram stain. And you notice on this top image, it's a very dark purple color. In the bottom, it's slightly purple, but it's kind of blotchy and light colored, and that indicates the filament is unhealthy and therefore is not staining as intended. But you could imagine if this process were to go on longer, this bottom filament may not look like Microthrix at all. In fact, Microthrix tends to get puffier, it loses things that are distinctive of it, like its Neisser staining properties, and it gets more and more difficult to identify, which means if you are seeing filaments in your anaerobic digester sample, and you have an integrated waste-activated sludge process, it's important to use that waste-activated sludge process sample as a reference for what type of filaments are likely to be accumulating. We've seen a couple of them. H. hydrosis I've seen a couple of times. Most filaments do not last very long anaerobically, but Microthrix has been kind of the big bad one we've seen. So here's a couple close-ups of it. You can see on the left, it has this kind of blotchy Neisser staining property, where you're seeing these Neisser positive granules and our Microthrix on the left. That's fairly healthy Microthrix. Whereas on the right, it looks kind of puffy and you don't see the granules anymore, which makes it a lot less distinctive as an identification. Which means you might look at filaments and say, well, there are filaments there, but I have no idea what they are. And a lot of people trying to do filament ID will have similar problems here. All right, so filaments usually lead to increased feeding or foaming immediately after feeding waste-activated sludge. Like I mentioned earlier, there's that example with the thermophilic digester. We were never able to get an actual sample of filaments in the digester. We knew they had a lot of filaments in their aerobic process, but they were breaking down very quickly in like 3 to 4 days. So they'd foam for like 2 days and then it would stop, and they'd be sending the sample right as it was stopping, and there'd be a couple unidentifiable filaments present. And we were just kind of like, well, what's going on here? I guess this filament doesn't live very long anaerobically. Levels of filaments, however, do not need to be exceptionally high in anaerobic digesters to cause foaming because of the high solids content present. The higher the solids content, the more capable the filaments are of stabilizing the solids to entrap gas and lead to foam. Like I said, filaments can survive up to a month. All right, so we're going to talk a little bit more about digester upsets and preventing an upset in anaerobic digesters. Monitoring is always the key. You want to look at biogas generation, volatile acid and alkalinity, very helpful for upcoming monitoring and predicting upsets. pH changes, sadly looking for pH changes tends to be a very reactive way to run your digester, and it tends to lead to not being quick enough. Your pH will drop to too low a point for the methanogens, and you end up with really big problems occurring when your pH really fluctuates. So you want to deal with volatile acids prior to the pH changing. Consistent anaerobic loading dramatically helps to reduce the risk of upset. If you're a plant that has high variability in your loading, you may want to consider, if feasible in your case, finding ways to stabilize that loading. Maybe it's scheduling when you're picking up different feed substrates if possible, or having an EQ tank constructed so you can increase the stability of your loading, because that'll help to prevent an upset. You're going to want to monitor and maintain healthy levels of trace elements and have a good understanding for your nutrient concentrations in your feedstock. And you want to be careful loading waste-activated sludge in your system, because it tends to decrease the surface tension in a digester and can introduce things like filaments. So if you notice a lot of filaments in your waste-activated sludge, you may want to reduce the amount you're feeding into the digester when possible. Another important note, if your digester has been sitting for like 30 years, it hasn't been cleaned out, there's a good chance you have a lot of inert solids accumulating in the base of your digester. And you might find if you were to clean it out that your digester volume could be like half of what it's normally supposed to be. Okay, so correcting an upset in anaerobic digesters. You generally want to make small changes to gradually move in the correct direction. So you make these small changes because if you make too big a change, you're going to end up with a stressed out population of methanogens trying to deal with a lot of food, and then your digester will keep falling into a state of decay and having problems. Alterations to mixing can help alleviate stress, and defoamers can be really helpful as short-term solutions as well for foaming and that sort of thing in an anaerobic digester, because as you're trying to stabilize your digester, foam is likely to crop up over and over again. Having a little on site can give you a lot more security, so you don't have to deal with a major foaming event. This is not an efficient solution for long-term, but this sort of thing is a great helper for recovering your process without having major foaming taking place. Another note that's very important to think about, if you have an upset, make sure to remember what happened last time, because there's a decent chance something similar will happen in the future. All right, pH adjustments and alkalinity. I covered this a little bit earlier, so I'm going to go through it fairly quickly. But be careful adjusting the pH when it's over 5.5 in the digester. For large pH adjustments, we recommend something inexpensive. But once you hit that 5.5 to 6 range, introduce something that has more bicarbonate in it. So we have our Boost and Lock, which you saw a couple slides ago, which is formulated to have several of these different compounds mixed together to prevent things like sodium toxicity I mentioned earlier, and also it will give you a decent amount of buffering capacity, so your pH is unlikely to skyrocket or drop off right away once you stop adding the pH adjustment tool. All right, so here's Boost and Lock. It's an alkalinity supplement. It has a number of different things. It will work for large pH adjustments, but it's more ideal as a maintenance and correction tool once you notice your volatile acid to alkalinity ratio has changed. Generally speaking, I'd like to have people add a small amount of pH adjustment tool more frequently rather than make giant pH adjustments regularly, because it'll keep your system a lot happier and healthier overall. All right, so we have our next thing. We have Quiczyme L, another product which we've used widely in anaerobic digesters, and I'll share some data on this in a cream sample after this slide. But Quiczyme L is a biocatalyst designed to rapidly break down fats, oils, and greases. And we use it a lot in aerobic process to correct for foaming filaments, so this could be a nice thing to consider if you see a lot of Microthrix. Quiczyme L is often an effective solution for Microthrix parvicella, which can help prevent the growth of these filaments and prevent feeding into the digester. We also have a lot of people using Quiczyme L anaerobically for digesters which receive high levels of grease. And we seem to be seeing pretty good results. And there's something slightly unintuitive there. So we did some studies to see how this actually would work in the field on volatile acid levels with the addition of Quiczyme L. So this was on a plant that was receiving large slug doses of cream, and we were looking at the volatile acid content and comparing with Quiczyme L to without Quiczyme L. And you'll see on the left, our control ended up with a lot of short chain fatty acids, whereas with the addition of Quiczyme L, we were able to totally eliminate these C6 and smaller volatile fatty acids, indicating that the digester was effectively uptaking the fatty acids, which might be a concern if you were adding Quiczyme L in some cases, because if you have lots of fats, it's possible you could end up overloading the methanogens, but we were never seeing this in the study. And one of the reasons for this may be that Quiczyme L helps to improve facultative digestion taking place. And this is an alternative process which could be good or bad, but it reduces the strain in a lot of cases on methanogens. And the happier and healthier your methanogen population is, the better your digester function overall is. So we generally have seen this work pretty well in practice for digesters with high levels of fats, and we haven't seen any evidence of it increasing the short chain fatty acid loading and causing a problem in sites. So another product to talk about is our anaerobic food supplement, which we have a recent BMP study. I mentioned biomethane potential studies earlier, where you're measuring the amount of methane production in a small reactor. And this supplement is ideal for stabilizing loading to keep an active population of methanogens in sites with inconsistent loading. So if you're not able to put in that EQ or regulate when your sludge feed is coming in, it's nice to add something like our anaerobic food supplement during periods of low loading, because it'll keep your methanogens happy and active so that when the loading does ramp up, they will be ready to handle it. So just for a reference, the addition of a food supplement in an anaerobic digester does basically what you'd expect to. The more food you have present, if your digester is healthy, you'll see more methane generation. And running this over the course of a month here, you can see we saw more methane generation with the addition of our anaerobic food supplement versus our control, which means that the anaerobic food supplement was an effective feed substrate for methanogens and was doing what we were hoping to see in the study. You notice a faster uptick in the methanogens. That means they were populating a little bit more quickly as well. So then we have a couple other products which we haven't traditionally used much in anaerobic systems, bug juice and Quicks IMP. Bug juice is designed to assist in the degradation of plant and paper materials in wastewater systems, and it assists in the degradation of fat, soils, and grease as well. We have some interesting studies that came out because we typically have used this in aerobic digesters, which tend to struggle with the degradation of fats in plant and paper fiber. But we did get some good data on that in anaerobic systems. And Quicks IMP is another compound, which I have some data on here, which we've been starting to experiment with more in anaerobic systems. Traditionally, it has been a product we've used for breaking down dairy protein in aerobic systems to prevent overloading and increase the availability of nitrogen. But we thought we'd try it in this study on a meat packaging industry to see how the Quicks IMP affected methane generation. And you can see here, the addition of both of these substrates, which are a biocatalyst product, led to a dramatically higher yield in methane relative to something like our food supplement. A food supplement will create as much methane as you're adding food, and that is basically it. But these increasing the availability of substrates, like you could have cellulose from manure, or you could have proteins from dairy wastewater, if you start to metabolize those more effectively and you're limited in your system on certain nutrients, like this system may have been limited on ammonium and free amino acids. So Quicks IMP appeared to help out with biogas generation fairly dramatically. I should mention these two studies were run by Digester Labs. We do a lot of partner studies, and they work with us quite a bit on biomethane potential. So feel free to look them up if you have any questions about anaerobic digesters. But you can always ask us as well. Let's see. All right, so I have a nice example problem here, just to get everybody thinking here at the end of the presentation and make sure everybody is still here, you know. So we have a Wisconsin plant which regularly has foaming problems during the winter. How do you identify this problem? So obviously, you might be concerned about temperature. I can tell you in this case, their temperature was very steady in the digester, at least according to their measurements. So then we also took a look at their mixed liquor sample and their anaerobic foam. And guess what? We're seeing quite a bit of filaments here. Look at that. There's a big mess on the bottom right of the screen with tons of filaments in their anaerobic foam. Clearly, this foam was some piece of the puzzle. All right, so I have one last poll here. What do you think was likely to cause the problem here? I get some opinions. We have a lot of people leaning towards filaments. Feel free to keep answering if you get around to answering the poll here, but filamentous organisms were clearly a piece, but we determined there was another issue when we were looking at the solids content in the digester. In this case, in addition to the filaments, they also were having issues with loading going disproportionately into their digesters. So they were loading one of the digesters that was foaming with a lot more solids than they were intending. So in this case, they had two digesters side by side, and one of them was getting more foam than the other. They both were foaming somewhat, which indicates the filaments were a major player to some extent. So good job to people who thought the filaments were a contributor here. I guess, but it's interesting because you have to keep looking at a bunch of different things, and you should never make an assumption as to what's going wrong in the digester, because initially if I hear about foaming in the winter, I think, oh, there's a temperature drop, and then I'll look for filaments. Hey, there's filaments present. By the way, Microthrix actually likes cold temperature too, so that would be another potential winter foaming issue you could see. But You can see we have very high levels of filaments here, and they were only a partial contributor to filaments. Filaments are very rarely the only thing in question, but they tend to contribute greatly. So it was just an interesting case. All right, so key takeaways from this presentation. Keep an eye on your loading and temperature changes because they will frequently lead to an upset. Fatty acid analysis in BMP studies are very useful tools for diagnosing problems and determining how to make changes in your setup. Also, keep track of your nutrient levels in the feedstock, very specifically, so you know if you're getting an adequate amount of nitrogen at least some of the time, and if you have adequate levels of trace elements. And don't just look at one number in the feedstock. Keep track of this over time, or make sure you're getting a high quality composite, because you don't want to be supplementing something that you actually have plenty of. It can tend to make problems in digesters quite a bit worse. Also, filaments don't generally grow in digesters. We look at the problem last case. They had a big food manufacturer discharging a lot of grease into their system. We can address that with Microthrix parvicella by adding the QuickSymL like I recommended to decrease levels of fats, oils, and grease going into the aerobic process, which should decrease the level of Microthrix and therefore decrease the amount that's fed into the anaerobic digester, fixing the problem more directly. All right, so here's some of our references. Let me know if you have any questions later on about any of these. And does anyone have any more questions? And I'll also answer a few of the questions that I left out and was going to get back to later. All right, the one that was answered or asked first in my presentation: is it commonly believed that quaternary ammonium cations inhibit methanogens by changing intracellular pH and depleting intracellular potassium, along with other enzymatic changes? In your experience, would you say that hydrogenotrophic or acetoclastic methanogens are more sensitive to the presence of quats? From my experience, so quats are interesting. They're a very stable molecule. They tend to not have much of an effect on pH in systems. As far as intracellular pH, I am not sure I know the answer to that, but I would like to look into it a bit more because that's an interesting point. But generally speaking, I would see toxicity to both hydrogenotrophic and acetoclastic methanogens if toxicity is in fact taking place. I find in a lot of digesters that are complete mixed, you aren't likely to have many issues with quat because your solids holding time isn't very long, and a lot of the quats are inactivated by sticking to acid-producing bacteria and facultative bacteria, which means they don't make as much contact with the methanogens, limiting the amount of problems they have. Now, one thing I would like to study more on this is lagoons specifically, because quats are known to be very stable molecules. If you have an anaerobic lagoon, it's possible that some of these quats, which would be bounded to dead cells in the anaerobic lagoon, would eventually be released as the dead cells begin to increase. And you could couple that with continuing inflow of quat at the same time, and then you might be able to lead to an upset in these cases. So that's a good question. I definitely am interested in the intracellular pH idea. But I haven't seen a lot of evidence in general of quats having a big effect on pH, and they tend to function more through direct contact in many cases. But I'm not necessarily, I don't know as much about anaerobic interactions with quats as I do with aerobic interactions with quat. What measures can be used to increase alkalinity in an anaerobic digester in addition to maintain a high feed pH? So alkalinity, generally speaking, there's also a question from Elok about increasing the settleability of sludge in aeration system. So the aeration system question, feel free to talk to me more about that later. There's a bunch of broad issues that could be causing issues with aerobic settleability. But as far as increasing alkalinity, I recommend routine supplementing if you know your digester has problems which would cause it to deplete its alkalinity and generate a lot of volatile acids. So maybe routinely feeding something like our Boost and Lock in low doses to make sure you have an established population of alkalinity to neutralize some of the incoming fluctuations in loading to prevent too much volatile acid accumulation, so you get to neutralize some of that. All right, is it okay to send you questions on TE and macronutrients after the presentation. Yes, definitely feel free to ask or send me any questions you have via email after the presentation. I would be happy to answer them. I can't promise I'll get to them immediately, but definitely in the next week I'd like to get around to a lot of the questions. I guess that would depend on how many questions. If there were like 50 that suddenly popped up, I guess it might not be possible, but I'll try to get back to you fairly shortly if you ask me any questions following the presentation. All right, well, I hope this presentation was helpful to you. And feel free to contact us about any wastewater questions or concerns you have, whether they're related to anaerobic digestion or not. We always like to have new wastewater problems to deal with. Though I do want to say, I do not want you to be dealing with problems. It's just that if you do have them, send them our way, please. Thank you. All right, everybody, have a nice rest of your day. Thank you for attending today's webinar.